little bit about Lakeside, founded in 1952. We have facilities here. The main office is in Mississauga. We have offices in Sarnia, in Guelph. As a matter of fact, the office in Guelph is going to be manufacturing facility is going to be moved to a new facility we just acquired in Dundas, Ontario, Highway 5 and Highway 6, I believe. And so a huge facility there to do a lot of our manufacturing, as well as valve service as well, because Lakeside will now be taking care of the servicing of control valves as opposed to Emerson. And we have also offices in Sudbury, Thunder Bay, Port Elgin, which I'm going there next week, as well as Winnipeg. And Lakeside is an Emerson-owned company. It's an Emerson Impact Partner, meaning we're the sole exclusive distributor for sole distributor for Emerson process automation products, and we're part of a 21 group of Emerson Impact Partners throughout North America. And our territory starts just from this side of Kingston to the Manitoba-Saskatchewan border and parts of Nunavut as well. You can see to the west is Spartan Controls, and to the east it is 𝗫𝗏𝗓𝗏 Controls, and obviously multiple ones in the States. And why do we do that? It's because we feel that this model actually provides you with better service, having a local presence as opposed to a monolithic corporate presence, and therefore we can actually serve your needs better. We obviously, some of you know, we sell a lot of stuff. I've never really been too crazy about this slide, but we obviously have multiple types of transmitters, analyticals, control valves, pressure relief valves, regulators, control systems. We do also a lot of welding, manufacturing, electrical services, instrumentation services, training services as well. And the whole idea here is actually to provide you with a positive customer experience. We really have this strong initiative this year to provide you with a strong, positive customer experience. Any feedback is always good feedback. I think at the bottom of our email signature, there's always a way to be able to provide us with feedback as to how we did. So we appreciate that. A little bit myself, I have over 30 years experience in terms of being in the field of instrumentation, process, and process controls. I do have a fellow named Andrew Poyton and Dean as well. Both are always available to help me out. Obviously, I do services within, I go to the field, do some loop tuning services, troubleshooting. I'm also responsible for advanced controls within 𝗪𝗓𝗏. Also do DCS alarm metrics, do some DCS alarms. Any one of you maybe go to your control room, you look at your alarm banner, I bet you that your alarm banner is probably full. I was just reading over 80% of the alarms generated by your control systems are probably what we call noise or nuisance alarms. And what we're there is I developed an alarm philosophy document and do in-depth alarm analysis to make the alarms relevant, as opposed, we don't want to eliminate them, we want to make the alarms relevant. And so that's a picture you see right here is actually not a stock picture. That's an actual picture we took at customer site that was part of their alarm silencing strategy. And I also teach courses. I teach a basic instrumentation course, which is about a 6-hour course, covers the basics of instrumentation world, the most common types of measurements, as well as got process control techniques 1, aka loop tuning 1, how to properly tune and scientifically tune control loops, and process control techniques 2, which is a more advanced course. As a matter of fact, this Feedforward lab you're going to see is actually part of loop tuning 2 or process control techniques 2. And I also do blogs. I haven't written one in a while, but if you go to our website and you type in blog or Confessions of a Looney Tuner, so you get these blogs that describe sort of technical stories that I've accumulated over the years. I try to make them light. I try to make them a little bit humorous, but at the same time, there is a moral to the story as well. So hopefully you go ahead and read those blogs. All right, so here we are. So we're going to go, why use feed-forward control? Feed-forward control really is one of the probably, I don't say misunderstood, but I think it's maybe underutilized in a lot of applications where maybe we can actually apply feed-forward control. We'll understand what is a load variable, a load disturbance, how to calculate the load gain, and how to tune a feed-forward controller. And we'll do that and also have we'll also have a live demonstration. So why? So, okay, let's say I got my controller. I got my set point, goes through my PID controller. That controls my process. I measure that process and comes back. That is my standard PID loop. However, I notice that there is this other variable, this other load variable, and every time it changes, it will affect me, the process. So therefore, if I can understand the relationship between here and here, maybe I could do something here to offset that load disturbance. The most common application I think most of us really understand for feed-forward control is in boilers. So here you got feed water coming in, usually under control, under cascade control from a level. You got steam generated. But we also notice this is a load variable that every time the steam, every time there was actual disturbance in steam, that it would affect the level and that would actually change the flow. So if we understand that relationship, let me just erase all that. So if I understand the relationship, every time there's a change here, maybe I should proactively make a change there because I know that load disturbance is coming. And in an ideal world, obviously, a pound of steam is equal to a pound of water. And so steam goes up by 1,000 pounds. I should add 1,000 pounds of water right away. And if I do it the right way, the right time, and the right amount, level controller should not see any changes. Obviously, this is an ideal. This is an ideal situation. In our example here, this is a different example. Here I have my process. So I have a temperature controller, and it manipulates a steam valve on a heat exchanger. However, I got product flowing through here, and every time there's a change in my product flow, it causes a change, a disturbance on my temperature. So now I have my process and I have my load. And so the key here is to be able to understand the relationship between the load and how it affects the process. If I understand that relationship, then I can build a feed-forward control to actually compensate for any changes in product flow. So in order to do that, we need to actually calculate a load gain. So if you remember way back when we talked about when I do tuning, I actually need to calculate the process gain. The process gain in this example, let me go back to here. The process gain would be the relationship between a change in the valve and how that affects my temperature. That's my process gain. And now after that, we need to understand the load gain. So how much of a change in flow will affect a change in my temperature. So the way you do that is that you perform a load disturbance. You would put the actual you will put the temperature controller in manual mode. There's a couple of different ways, but this is one of the ways to do it. And I would change the product flow. So you can see here, I changed the product flow. And this is the output of the product flow, the output control valve that controls the product flow. And you can see here, the temperature decreased. Temperature decreased. So now we need to understand, therefore, that change in product flow, delta L, caused a change in my temperature, delta Y. And everything's got to be, again, you got to watch out for your units. But most of the time, most controllers nowadays speak in the universal language of percent of span of the delta L as well. And therefore, KL will describe the how much of a change in load causes how much of a change on my process. So how does a feed-forward controller work? First of all, we know that when there's a change, every time there's a change in flow, it will affect the temperature. So what we need to do then is calculate the feed-forward gain, KFF, so that that branch here will cancel out that branch, and therefore there should be no disturbance perceived by the PID controller. How do you calculate? KFF is equal to minus KL over KP. So the ratio of the load gain to the process gain. And note the negative value as well, so the minus sign as well. Because in our example, an increase in the product flow causes a decrease in our temperature. And the reason for that is obviously there's less residence time going through the heat exchanger, therefore less heat will be absorbed, therefore the temperature will drop. So that's how you calculate your feed forward gain. Now you got to be careful again. This is probably more of an ideal number. We have to be careful, and I'll show you some of the pitfalls you can run into later on. So I'm going to go through here. So this is the actual same picture I just showed to you before. There's my flow controller, and there's my temperature controller. And my temperature controller, right now, I'm actually going to, they're all tuned up, but I'm going to make feed forward. Oh, that's right. I can only change it while in manual mode. That's because it's in velocity form. So I'm going to change that to 0. So now I have no feed forward gain at all. Now, this is the bumps I just did earlier this morning just to save a bit of time. So the yellow line here you see is the temperature. The white line you see is a temperature set point. The blue line is the output of the temperature controller to the control valve itself, this valve right here. And the orange line is the product flow. So it is this flow coming through here. So let me go back to here. And you can see here, I did a change in product flow, and the temperature controller was in manual mode, and the temperature, as I slowed down the product flow, the temperature went up. So to calculate my load gain, I would see how much of a change in temperature that I get for a given temperature change, given flow change. That will be my KL. And I did it twice right here. Afterwards, this is where I really want to show the advantages of feed forward control, is that then I put the PID controller, the temperature controller, in automatic mode. And I perform a load disturbance. So I decrease this flow going through here. And then let's see how the temperature reacted. This is with no feed forward control at all. And you can see here, I did my load disturbance right about here. Now, one thing I want you to understand as well is that in this temperature process, I built in about 8 seconds of time delay between the moment I make a change on my steam valve and the moment I actually perceive a change in temperature. It could be from anywhere from low heat transfer dynamics and transportation dynamics. So I have 8 seconds of time delay. And you can see here, I did a low disturbance. However, the temperature only started to change 8 seconds later, and my PID controller alone, no feed forward, started to react then. So you have to understand, I'm actually 8 seconds behind, or whatever the process dead time would be. So afterwards, I put in a feed forward gain of 0.625. And I'll explain that 0.625 in a minute. And then I made the same load disturbance. And now you can see, so feed forward says, okay, someone told me, I don't know anything about PID controller. It's just someone told me when this changes, when the flow changes, I need to move the output by this much. I don't know why. Someone just told me that. I'm not very bright, so that's what they told me to do. And so here, as soon as the load flow changed, you could see that the feed forward started reacting right away. It didn't wait for the 8 second time delay, process dead time. And then therefore also helped out with the PID controller. And you can see here, without the feed forward, I had about a 9.5 degree deviation between the temperature and the set point. With feed forward, I had 4.8 degrees variation, almost half. So you could definitely see that being proactive and actually acting upon a change in disturbance right away, feed forward can certainly help. Now, I said there can be some pitfalls with the feed-forward calculation. Is that ideally, in theory, when I calculated this, the actual feed-forward gain should have been around 1.25. So, however, if I were to put that in, because actually this process is actually a little bit nonlinear, my process gain actually changes based on the flow rate. So the process is not super linear, and let's face it, there are really no true linear processes out there. But in this example, if I did put in the true theoretical feed-forward gain that I should have put in, what happened now is that you can definitely see an overcorrection. You got two controllers fixing the same problem, and it overcorrected. And that's what we need to be careful. Is whatever theoretical feed-forward gain you actually calculate, we need to back off a little bit. And I even say that even for boilers. A lot of times we'll see a feed-forward gain on the boiler to be around 1, because as I said, a pound of steam is equal to a pound of water. And a lot of times it works, but I'm always more comfortable on kicking back on the feed-forward gain to maybe 0.8 or maybe 0.7 and leave most of the job to the PID, the feedback controller. The feed-forward will help you, but most of the job will be left to the feedback controller. And that's what I wanted to show you. And so what I'm going to do here is I'm actually going to, still a manual, so I got to put this to, and I just want to demonstrate it quickly. 0.625. There we go. So I go back to automatic mode here. Bring this up again. So now what I'm going to do is I'm going to change the set point on the load flow. So 350. Now, as you can see right here, as soon as the load flow changes, the output to the steam valve changes right away. And you can see here the process only started to react 8 seconds later. So you can imagine you have some processes that have very, very long dead time. I'm thinking for chlorination in a water treatment plant, you can have 45 minutes of delay. So you got to be cognizant of that. Or a pH, where maybe the flow is changing, and therefore we have to probably wait till the neutralization has to happen before we measure the pH. So there can be some significant process dead time. Feed-forward would be certainly a good addition to actually getting better control. And you can see right here, it already started to turn the corner. So let me go back to here. So once again, I'll just show you once again, without feed-forward, definitely a long deviation. And again, you can see here where the load flow changed, but took a bit of 8 seconds before there's actually any kind of reaction when there's no feed-forward control. There is a time delay. Whereas with feed-forward, there is no time delay. So as soon as the load flow changes, I move the output right away because I know that disturbance is coming. And once again, went from 9.4 degree deviation to 5.1, give or take. So a significant improvement in low disturbance rejection. And once again, kind of repeating myself redundantly here, too much feed-forward can result in overcorrection. You got two controllers, you got a union jurisdiction problem here, two controllers fixing the same problem. And now what's happening is that you get overcorrection, and it could potentially destabilize your controls. And that concludes this webinar. Hopefully, we'll see you next one. We'll talk next month, November 17th. We're talking about split range control. And split range control is that one PID controller controls two valves. Typically, one opens first, and then the second one opens later. It could be third or fourth. and then we'll discuss that and how to properly adjust the split range based on the valve characteristics and sizing. So I'm going to open it up for questions, and I know there's a 10-second time delay, so I will pause. Oh, I know there must be some questions out there. Okay, I do have a question. When you talk about two controllers trying to control the same valve, isn't the feed-forward option built into the PID block, so it's just one controller? Well, I guess technically, no, it's actually composite. So when you enable the feed-forward, it actually is itself strictly a ratio controller based on the load variable. If I can actually, so therefore, it is two controllers outputting, and you get the sum of the output of the feed forward and the output of the PID block becoming the true output to the control valve. So technically, I guess what you're saying is that if it's one block, it's one controller. I can see what you mean, but really there's actually two controllers, a feed forward controller and a feedback controller, a PID controller within the one block. Hopefully, I get another question. Another question. Does a feed forward KFF affect the PID tuning parameters? That's an excellent question. Um, my answer is no. The first thing I would tune, obviously, is the PID controller, the feedback, because it is really the primary controller. It does have the feedback. The feed forward is just a bit of a clueless, a bit of a dummy. All his job is to say, well, when this low variable changes by this much, I'm going to add this much to the output. So if anything, you could, if you I would typically, not all the time, but typically I leave most of the job to the PID controller and have feed forward controller just give us a bit of a help. So another question, can you show some sample configuration? Absolutely, I can do that. Just bear with me right here. So if I go right here, oh, not this one. That's not what I wanted. This is the one I want right here. No, that's not what I want. So if I can view, zoom in, and then therefore I can probably make it large enough for you. There's the PID block right here. So this is the input here. So I built in 2 time constants to be able to simulate my temperature. And there's my feed forward value right here. And the feed forward value comes from the flow. And therefore that is actually the flow coming into here is actual configuration for the feed forward block. Oh, you guys are coming in with more questions. Awesome. Do you think feed-forward controllers should be used more often or only relegated to rare applications where PID is not working? Are there any dangers in using it? I do believe actually that it is underutilized. And as I just demonstrated also, I do believe that especially for processes that have significant amount of dead time, and we have the luxury, we can characterize a load variable that affects us, our process with lots of dead time. I do believe that it's actually very beneficial to use feed forward, because then we can preemptively catch the disturbance as opposed to wait for the dead time to expire before we react. Can you use feed forward controls if the process has a big time? I think I just kind of answered that question right now already. Is that especially with dead times, I think feed forward would be very, very advantageous. Like I said, because then we can proactively react. We know that disturbance coming down the pipe. If we characterize it properly, we know then we need to react right away. Those are great questions. Let me see if there's any more questions. Another question here. So do we have another process variable that we use to predict the coming change to our process that we're trying to regulate? Yes, it is. It is another variable, another process measurement. Therefore, it can be a calculated value. They could give, like if it's a concentration of some sort, but we have to have some other measurement. In this example here, it was product flow, and we understood that a change in the product flow affected my other process, my temperature controller, and that's the relationship we need to establish, and that then leads to the calculation of your feed forward gain. Another question: can we use feed forward and PID block, which are master and cascade control, basically driving the set point rather than the valve or pump? Absolutely. That's how exactly a boiler drum level, 3-element drum level control works. Is that if the steam flow goes up, then we're going to increase the set point to the feed water flow controller because we know that disturbance is coming. Absolutely. Another question. Is a function available with all controllers in Delta V, or is it something that would need to be configured for the specific controllers? No, this is actually right out of the box. So when you plunk in a PID block, in your configuration, it already comes with that. The only thing to do is just enable it. So if I go down here, see at the bottom left-hand side, feed forward enable is true. And so therefore, you just got to enable it. That's all you got to do. And there's my feed forward gain and feed forward scale. You guys are great. Doing a really good job. Great questions. We'll give it another couple of minutes. Make sure that we answer all the questions. And as I mentioned, if you think of a question afterwards, you're more than welcome to reach out to me via email or cell phone. And also, just a reminder, we will also be sending you a link of this presentation. You'll probably receive it probably mid-afternoon. So I got another question here. So to compensate delay, which do you suggest, Smith predictor or feed forward control? That's a bit of an advanced question, actually. So the question is, to compensate for time delay, is it better to use a model-based controller, one called Smith Predictor, which is interesting because I will be talking about Smith Predictors. I believe it's my last webinar, number 10, or use feed-forward control. My answer there will be probably feed-forward control. And the reason being is that I like to try to keep things simple. I've been doing this for 30 years. And engineers, sometimes, you know what? We tend to overcomplicate things. And what I like to do is try to keep things as simple as possible, and probably considering the feed-forward control. Again, it would depend on the application. So, and that's some application where maybe we do not have a measurable load variable, then perhaps Smith's Predictor would be better. If we do have a measurable load value, then perhaps feed-forward control would be better. These are great questions. I'm really enjoying this. Like I said, we'll just give another couple of minutes. This is all right. As I mentioned, if you have any questions that you thought of afterwards, turn my camera on here. So if you have any more questions later on, feel free to give me a call or give me a shout or drop me an email. Thank you very much all for attending, and I certainly hope to see you my next webinar talking about split range control. In the meantime, stay safe, stay healthy, and we'll see you later on. Have a great day. Bye now.